Okay, hi everyone. Thank you for spending time to the TILOS seminar series. And it's a great pleasure for me to introduce Dr. Professor Maarten Vlasov. And he's a Simons Chair in Computational Applied Mathematics and Earth Sciences at Rice. He's internationally recognized for his contributions to mathematical foundations of seismology, wave propagation, and inverse problems. His research bridges microlocal and harmonic analysis, scattering theory, structured numerical methods with applications to seismic imaging, geophysical inversion, and large-scale computational modeling of acoustic, elastic, and electromagnetic phenomena. Dr. De Hoop has been a pioneer in developing techniques to extract subtle information from massive, complex seismic data sets and advancing our ability to probe the Earth's interior with unprecedented resolution, and more recently has integrated deep learning and data-driven methods with rigorous mathematical foundations to open new frontiers in analysis of multi-scale wave phenomena and inverse spectral problems. My connection with Dr. Maarten De Hoop is like shortly after my wedding, I ditched my husband to join an expedition with Dr. Maarten's team to Iceland. And we went, and that was the best trip and eye-opening research expedition I've ever had. So since then, I have stayed in touch with Dr. Maarten, and he just been so inspirational working in the intersection of AI and science. So today I'm so glad that you are coming to visit us, and let's welcome.
Thank you, Rose. And yeah, we have good memories of Iceland. We did a few of these in different parts of the world. But there were serious meetings. These were good locations, but serious meetings, right? Yes, great. So thank you for having me. Thank you for the invitation. Great to be here. And before beginning, I would like to say there are various students, postdocs, and collaborators involved that I will talk about today. I would like to highlight that a lot of this work started when I was in Paris at École Normale, working with Gabriel Perret, but also people that were big contributors to this were Michael Mahoney in Berkeley and Ivan Dokmanic in Basel, and I will come to others as we go along. So this talk is going to be a very basic talk about foundation models. And the question I ask is the following. What we would like, or what we are interested from a foundation model, is the following. Can you design an architecture that can be pre-trained on massive sets of data from physics, different kinds of physics? And I have lots of data, so I can do the pre-training, as you typically do, like in a large language model or the like. And then I want to fine-tune it on experimental data that are very limited, small data set, and try whether I can then infer physics from that small data set. So in other words, is there a foundation model that sort of provably can maneuver between different fields of physics? And I will argue that if you follow the basic building blocks of foundation models today, in particular transformers, the answer is not quite yes, you need to intervene. And I will talk about how I get to that conclusion, and then I'll talk about how I propose to intervene, and then give you a couple of architectures that go in the direction that show performance along these lines. You may ask, why am I interested in this? Well, I'm very interested in this in terms of learning earthquake dynamics, fault dynamics. So the problem of learning fault dynamics, earthquake dynamics is we have extremely little data. The data that you would like to have should lie densely over the faults, the active faults where earthquakes happen. But of course, they happen scarcely. The bigger ones happen scarcely. And so there's never been the funding to instrument faults on the scale that you would need them to directly apply learning methodology to them. And so the question is, with the data available, sparse data available here and there, pockets sometimes far away from faults, and laboratory data, could you actually learn something provably in this way by making use of very different kinds of physics to sort of pre-train a model, like what you do in foundation models? So could it at all be possible? So I would like to go to the very basic building blocks and argue that kinetic theory plays an essential role in getting these insights. oops, let me see. Oh, this works. And so here's the diagram, pretty much the outline of my talk, and I will sort of detail certain aspects of it. And so, as I said, I will go through a basic viewpoint, and I'll start with the basic idea what a transformer is built from, and go through a measure-theoretic viewpoint. To do that, I'll explain why, and look into transformers from the viewpoint of in-context maps, and then argue that, in fact, that leads inherently to interacting particle systems. And in some sort of analog to a mean field limit leads necessarily to a Vlasov flow. And so essentially transformers from a physics point of view and a mathematical point of view act like interacting particles. And so that part of the talk, I'll take a more theoretical, detailed approach to argue that this is exactly how it works. But there's then the dichotomy, because Vlasov interacting particles are not very good via some sort of method of taking moments, for example, to create laws of physics that we're familiar with. For that, we need collisions, collisional dynamics. And of course, that goes back to the celebrated work of Boltzmann. And so there's an incompatibility between Vlasov and Boltzmann. And that is the very essence where transformers sort of stop directly to be useful, and why we need to intervene to do something much closer to Boltzmann in the architecture, to have an architecture that, like Boltzmann, by taking moments, can lead you to fluid dynamics, magneto hydrodynamics, granular flows. It can even recover the Dirac equation. It can do cosmology. Can we actually come up with an architecture that mimics that idea? And so I'll talk about that transition going from a Boltzmann instead of a Vlasov perspective to architecture. Yes.
So you're seeing transform maps into an interacting particle system. Then you make them a non-interaction by doing a mean field approximation.
Right.
So then you end up with a Vlasov theory, then, which no longer has interactions in a
Correct.
genuine way. Then you're saying then you try to put them back in again to get a proper Boltzmann description.
I try, yes. So the mean field is indeed the outer part to the argument. The inner part is I want to replace interactions by collisions.
Yeah.
And of course, there's a massive theory in kinetic theory, in particle system theory, how to do that, like the Boltzmann-Grad limits and the like. I wouldn't want to go into these details. The story is there a direct path to do that by intervening in the transformer architecture? And that's what I mean. So the mean field is an argument, where's the kinetic theory in the background to motivate what we should do at the architecture level. Yeah.
What is the analog of the low density limits that you would use for kinetic theory in the case in the language of transformers?
Yes, I will hint on that, how we do that in an architecture that we introduced called NERDY. But there's no comprehensive answer to that yet in the story. So the story is, I will hint to that, but I cannot give you the complete story at this moment yet. Yeah, very good question, a very important question. Yes. And so I'll go in that, and I'll give sort of the fundamental idea that we can understand by essentially introducing a stochastic viewpoint. Yes.
Vlasov perspective is actually important for running out probabilistic distribution.
Sorry, why the Vlasov is important?
Yeah, I'm just like not familiar with the term.
Yeah.
Just perspective on like why this insight or this perspective helps.
So the perspective helps. So I will come to that. I'll explain it in detail. There's an inherent connection between attention and interaction of particles, say potential of interacting particles. And my argument is that is not a good viewpoint to actually represent physics. And the limit to go from particles that do not collide, but only interact versus particles that actually collide is a complicated limit that has been studied from a kinetic theory point of view. And here I propose that we should do that on the network level as well. And that brings us to a right physics perspective. So I hope that it helps, but I'm going over the details, and hopefully you ask the question again when we get along. Happy to do that. Yeah. And so I'll introduce the notion that we need to introduce a certain stochasticity in the network, and that will go via Poisson measures. And then that's the more theoretical part, half of the talk. The other half of the talk, I go into some sort of more practical ways. Once we know that, can we come up with proxies of networks that mimic that at this point? It is very much an evolving field. We have sort of two branches of networks that beginning to do that actually can be engineered. We would like to do more, but the transition to go from these architectures to standard transformers is significant. And I hope I built a case that this is the right direction. That's the main conclusion, if you wish, of my talk. And what plays a very big role in order to make this work is the notion of entropy, an abstraction of entropy inside the networks. So that is sort of the story that I would like to go through. Again, I will do the first part up to Vlasov, what that fundamentally theoretically means for the people that are more theoretically oriented, and then I'll switch gears to the engineering side, like how the actually architectures emerge by taking a different point of view in the second half of the talk. But stop me with questions anytime. I don't have to go through all the materials. I can just talk about any aspect of it. Oops. And so let's start with the upper part of the diagram. And so this is joint work with Gabriel Perret and Takashi Furuya in Japan. And so essentially, summary is I will formalize the transformer's expressivity. I think I'll dive straight into the theory. And the question I want to ask by formalizing it, understanding really what transformers from a more general perspective are, the first thing you want to remove is when you input into a transformer a finite number of tokens. A lot of theories were built around this fixed number of tokens. When we talk about physics, the number of tokens is irrelevant. And so we need to make it invariant under the number of tokens. That's the first argument. In fact, I should be able to work with an infinite number of tokens. That requires a switch to look at transformers instead on working on tokens, on distributions, on probability distributions, I will explain. And then I do that in the beginning, and then I'll ask the question, what is the closure of transformers? So in other words, what sort of maps between probability distributions actually are transformers? These are all the transformers that you can ever imagine, and they have certain regularity properties that are very interesting, that are Vlasov-like, but that's not what you want from a physics point of view. And so that is sort of where we'll go with it. So quick, yes, question.
So when you apply transformers to distributions, is the idea that the tokens are sampled independently?
The idea is that the tokens are indeed sampled from that distribution. So instead of thinking of a sequence of tokens, I'll sample them from a distribution. I'll precisely introduce that. Then, of course, a question will arise, well, you can do that, because if you have an unmasked transformer, the permutation of the tokens doesn't matter in the process, but we can actually make it causal as well. We can generalize the notion of masking. That's technical. I have slides at the end, but I've not planned to talk about it in view of time, because that is an interesting aspect of it, but it leads to technicalities that can be covered, but I will skip. But the answer is yes, that's what I'm going to do. And so notations, standard notations, I think I don't have to say much, how I introduce sets, how I introduce component-wise multiplications, identity factors. Then probability measures are always defined on a domain omega. I always forget to mention that a domain has to be compact in all the arguments, so I have said it once and for all. And these live in RD. So think of D as the embedding dimension of the tokens in traditional language models. So that is now fixed. So that dimension of the embedding dimension is fixed. And P omega are the probability distributions. And
examples where the domain is not common.
Well, that's a good question. I would say it arises because it is very hard to prove anything if it were not.
Yes.
So I'm not sure if there are practical
Vision or something like this.
Yeah.
It's hard to imagine the domain is common.
Right. Yes. Yeah. And otherwise you need to carve out a compact domain in which its behavior can be done. But yeah,
It's a extension.
there are technical extensions, and some of them can be done that I put aside, but generically this is sort of the framework where things can be formulated. Yeah, there's a good point. Yeah. And so a quick notion, the notion of push forward. So a push forward here, if you're not familiar with it, take a sum of Diracs, let xi be tokens, write the tokens as sum of Diracs, then the push forward is nothing else than mapping the tokens to new locations. But from a measure-theoretic point of view, if I have a measure, a probability measure, push forward is essentially defined in this way, by this integral. Take a continuous function, you integrate the function against the measure, and it push forward does that essentially via pullback. So think of a push forward of a measure just as a way via integration. These two things, of course, when you substitute the Dirac, are the same thing. Right? They play a fundamental role. And I need a notion of convergence to describe what I'm going to speak about. I use the weak star topology and the probability measures, which is associated with this notion of convergence. So you take continuous functions, you integrate the continuous functions against the sequence of the measures, and it converges in terms of integration. That's essentially what weak star convergence means, the weak star topology means. So it's a soft notion of convergence. And so in the case of discrete measures, I can just substitute discrete measures, work it out. It really means that, in fact, if I take the collection of tokens that I write as uppercase X as a matrix, where the columns are the tokens, then essentially the sequence of the collection of tokens converges column-wise to the tokens, the final tokens of the sequence. So these sort of things coincide. It's a pure notation.
Are you actually referring to the sample size?
Little n refers at the moment to the number of tokens. Yeah, the contact length, exactly. But that contact length is going to disappear. That's sort of the key point. But now it is the contact length. Yes, that's correct. And so here, you're probably very familiar with it, but I'm going to manipulate this. This is essentially the definition of attention. And so what I'm introducing here is the matrix X. Everywhere X is the matrix where all the tokens, the entire context is put together into a matrix. So X is always the actual tokens. And the tokens live in a token dimension, D token, RD token, and so forth. Then the attention is basically in standard way. I take the tokens, I multiply it, of course, with a key matrix. I multiply them, I take the transpose. With the query matrix, I take the dot product. I normalize by the dimension of the key and the query matrices, the spaces in which these map. And I take the softmax and then, of course, multiply by the matrix of tokens and then the value matrix, where the softmax is defined in the usual way, the exponent way. So I assume that you're familiar with it, but otherwise I'll be happy to answer questions. What I put in here is if I introduce masking, then the masking effect is just that I multiply by the matrix, where essentially you have the lower triangular matrix. So it only looks from one direction into the sequence of tokens. So it just look in the past and not look forward, if you wish. That's how causality is built in. And that can be built in throughout the talk, but I'm going to skip this. So we are essentially looking at bidirectional encoding transformers in the strict language of machine learning in this talk. And so I have these attention mechanisms. I introduce then heads standardly. So I introduce, say, H heads. And what the heads do is I take many heads and I basically mix them. I take a linear combination with a matrix WH. And last but not least, I introduce a skip connection, which is standard, to get what I call the multi-head attention. So I've done nothing here, just introduce notation for multi-head attention, how it would look like in a standard transformer block. And so this is sort of the picture. So I have tokens X, and I want to predict, I give you a probability of pulling out or predict a token as the output of not of one layer, of even a deep transformer. And I would like to describe that process via the introduction of an in-context map. So I'm going to intervene and write subtly the attention a little bit different than the standard way. And I do that as follows. So I copied over here at the bottom, essentially the multi-head attention, as you've seen it before, but did one difference. I let it depend. So on the right entries, I substitute the tokens, the XJs. And so that is indicated here by X. So uppercase X is always the sequence, if you wish, the collection of tokens altogether. But little x is a free variable. So this is not a token at this point, it's just a free variable. So G theta is, well, a function of the tokens and a function of X. And so basically I split that in this way from the attention. And so he said, well, there's a weird way of writing it, but if I do the following, I take the in-context map, what I call the in-context map, and I substitute for X just the tokens, then I get back to multi-head attention, right? It's just a notational trick. Nothing has happened. So essentially, this is the attention mechanism. So G contains all the weights, the key, query, and value matrices, depends on the tokens themselves, and can this be seen as a parametric map that is modified for each token depending on its interactions with all the other tokens. And so now I can define a composition of these. And I want to translate a composition to generate a deep transformer via a composition of the in-context maps. And so what I intertwine standardly is, in transformers, we always introduce a multi-layer perceptron. So let's do that. This is a standard multi-layer perceptron. This is basically a contract-free map that I just introduce as if it were. So the dependence on the tokens is removed here, and it acts independently of each token. So just each token gets subjected after the output of the attention to an MLP in parallel. It's a standard way how it works in transformers. So this is the little f, and so this is what the composition would mean. And so how can I translate that into the composition of the in-context map? Well, as follows. So start with the first layer. So here's my in-context map, G1. So now how I go to the second layer, I substitute for the variable x, G1 xx, where x is a free variable. These are the tokens. And here I have x1, and x1 is actually the outcome of translating the in-context map into an attention representation. And that composition I call the diamond composition. It's not hard to see that that is the new in-context map after I compose two layers. And I keep doing that, and I can put in these multi-layer perceptrons. I do that, and via this diamond decomposition, I get my in-context map of a transformer. So this is just changing the viewpoint of something very, very basic. And so now the core question concerns, first, so what is the closure of these objects? So in other words, what can this uniformly approximate? So if I put attention there, what sort of in-context maps can be uniformly approximated by attention maps, right? This is the first question to begin to answer the closure question in the right topology. For that, we're going to switch gears, as I promised. We are going to say, well, I want to have it independent of the number of tokens. So I'm going to replace the tokens, the matrix X, by, as I said, a distribution, a probability distribution that actually represents pulling the tokens from that distribution. So I'm going to replace the matrix X by a measure mu. And so instead of working on discrete tokens, I map between measures. And I do that in a way that if I substitute Dirac, so they get the same back. And so here are these probability measures. And of course, my claim is I design it so that if I replace the probability measure by a sum of Diracs, then I get back the old mechanism, right? So how do you do that? Very simple. The new in-context map, that I don't call G anymore, but call gamma here, is now not summed, but integrated over the measure mu. So the matrix X of tokens is now replaced by the measure mu. The X variable is in the same spot as it was before. So here you see the skip connection. And so instead of the summation, you have an integration against mu over here, and the normalization is softmax and that. So this is basically the form of an in-context map. And so, well, I said this before, abuse of notation, this in-context map depends on the distribution and the free variable, the vector x, but I usually write it in this form. I think of it as a map that depends on the distribution and is then viewed as a function of x. Okay, so I can sort of manipulate it, right? And so then comes the story, what is a transformer? It's nothing else than a push forward. So transformer is nothing else. What I do is I evaluate the in-context map at the measure mu, and then I push forward the measure mu by that in-context map. And so the mu appears here and here. That's essentially what self-attention in the context does. So this is for a deep transformer. This is everything it is. So now we have a very clear, clean mathematical object that allows us to study what transformers really are. And I haven't really changed anything other than the number of tokens is gone, and I work with distributions rather than with sequences or finite sets of tokens, right? Yeah.
So when transformers are applied to text, usually the actual sequence is very important. And position is encoded
Yes.
very carefully.
Right.
So that's not a consideration.
It is, yes, very good point. Positional encoding. Could I build it in? Yes, I can build the positional encoding as a weight inside this exponential. But I stripped this off, like I didn't do masking, I didn't do positional encoding to try to keep the talk as transparent as possible. Yes, you're absolutely right. Positional encoding sits in there, can be included in here, as well as the masking, but it becomes a whole lot more technical. But it works. Same idea works. It's just a matter of technicalities. Yes, very good point. Thank you for bringing that up. Yeah.
And then you replace that with the probabilistic measure, then you basically assume we have infinite context maps now, right? Because look
You
at
could. Yes, you could, like it is undetermined, right? Yeah, I can substitute a finite set of Diracs and it's completely legal, then it's finite, but I don't have to. And that's what you want.
No, that's not what we want.
Well, in physics, let's put it this way. Yes.
One that described to us the limit of approximation as a function of context maps and also as a function of the sequence, right? So that's kind of important.
Yeah, well, of course, but in physics, that's quite different, right? You want to be robust because in physics, the number of tokens plays a very different role. So you want to be invariant under the number of tokens. It's easier to get it dependent on the number of tokens than it is in without. Yes.
Aren't you, and previous question, aren't you in a sense making probability measures over objects defined on space as well?
Yes.
The order comes from the spatial structure of the measures. Right?
Correct.
So then,
yes.
Then in that case, so if you generalize this in that way, which is very natural to physics, then you would have a universal function.
Yes.
Right.
Exactly. That's my claim. Yes.
Why I didn't understand why there might be a problem.
No, but I guess my question is like ideally I would like to see like we would keep as a function of n the long term.
Yeah.
But then in this case, if we sum over n, then it's no longer dependent on n. Because your g function is just the aggregation of everything.
So you just have to then you just have a continuous basis functions rather than just a spin one.
Exactly. That's exactly what it is. And so the sum over the Diracs, forget about the fact that on a measure level it becomes a sum. It is not the sum, it's just the n that appears. So if you want to do it for a finite number of tokens, it is just the number of Diracs in the sum that appears. So I think it's just, it's a little bit subtle. If you substitute for measures the sum of Diracs, that sum is just representing that falls out actually as the tokens themselves. Yeah. So I think, yeah.
I think that's
Yeah.
But this is like building a basis set of a bound states which are discrete and also including continuous states.
Exactly.
And so altogether you form having a universal function.
Exactly. It's exactly the idea. Yes, you articulated better than I did. Yes, exactly what it is. Thank you. I'll try to remember this and next time. Yes. Great. And so, of course, on this level, I can introduce a diamond composition, make the network deep as I did before, and so forth. And this is then the deep network analog on the level of probability measures. A few things, you can prove things on the regularity of these objects. For example, you can prove that this in context map is Lipschitz regular in the Wasserstein 2 distance. You can make that quantitative. If you do it on the level of general measures, the estimate, of course, is much worse than if you work in context with only n Diracs. So, for example, if the supports of the measures, like say in a ball of radius r, and I work on general measures, then here I have an exponent that's a function of r. But if I work with empirical measures with n Diracs, it is just polynomial or quadratic. So these constants, of course, the Lipschitz constants, of course, are drastically affected by the generality of this, and you can navigate it. And you can do that for mass attention with conditional optimal transport. So there's ways of studying this regularity, but I leave that aside at this point. And so here's the... No, but it comes out. So so you don't need it. That's right. But it's and this is actually one of my points will come in fact in this theorem, that the in context map that you generate via attention is in fact continuous, is uniformly continuous. Vice versa, any continuous, this is sort of the statement of the theorem, any uniformly continuous in context map, in fact, can be arbitrarily well approximated by making the network deep enough, by making it deep enough. And so that is good and bad from a pure conceptual point of view, of course, continuity is attractive. From a physics point of view, it is actually not. That will be the moral of the story. But yeah, so the story is, so the context map works on the product space of probability distributions and the domain. And so the topology is in the weak star topology. And here's the approximation. So basically the closure or the universal approximation results. And the key point is that in the approximation, we don't have the necessity to let the dimension of the embeddings of the tokens become large. It can be bounded just by the dimension of the input and the output vector dimensions. And the number of heads can even be 1. So the number of heads doesn't have to be taken arbitrarily large. So I don't have to take any sort of mean field limit in terms of number of heads. And so the key point is that this is completely independent of epsilon. What I do with these dimensions, you can keep it even if these bounds. And so that is sort of the key point of the story so far. So this is sort of the description of what is going on under the hood of transformers. I can do it for the mass case. I'm skipping that. If people are interested, I can give you the slides. And so now I want to come to the next point. And the next point is now we notice what is actually the closure. So now we think of the picture that we act on probability distributions rather than tokens, as we have discussed. So essentially a transformer is a mapping from measures to measures, probability distributions to probability distributions. Which maps are transformers? So what's the closure? And so let's go over that. And so this is a surprisingly technical matter that I will not go into detail, but it gives you a flavor of what the technicality is. So let me introduce carefully first positive measures. That's P, probability measures. It's easy to work on positive measures. I introduced them from the probability measures via scaling with a positive constant. Then I want to introduce the set of measures that consists of a finite number of Diracs that I call m plus n, where the weights, the coefficients are positive. And then I want to consider the set that contains all possible in context lengths that I call m finite, where I take an arbitrary number of tokens in the sequence. So this is sort of how I introduce these particular measures. So bear that in mind. Now what I do is I do something strange that is coming soon. I'm going to introduce a strange topology. The first topology is standard. I use the Wasserstein 1 topology between the measures. And for positive measures, I build that in via the scaling as 1 as 2 in the simple Euclidean way, right? So that is setting the stage, the basic stage. Now, in order to get to the result, what I need is the set of Diracs that are different. In the following sense, take two sets of Diracs, so mu's that are Diracs, that are described by the weights AI. Consider two subsets from 1 to n, such that these subsets are not empty, but have an empty intersection. So do not intersect. Then if you take the sum over these sets of the weights of the Diracs, that these sums will be unequal. So that's what I call, if that is the case for the elements, then I call that the set m plus finite different diff over here. And then I can remove the dependency on n by taking the union of all lengths, and that I call that. So this is a very strange set to think of, but now you can prove that that set is actually dense in the set of positive measures in the Wasserstein topology. So by taking that assumption that allows me to understand the closure, in fact, doesn't harm me. I can claim that I can do it on any positive measure. So that is the first lemma that you can prove. And so now here comes a definition that will lead to what the closure really is. The first thing is support preserving. You will not be surprised that if I take a transformer, I feed it n tokens, n Diracs, that n Diracs need to come out. Well, modulo multiplicity. That's what we call support preserving. So that's precisely described over here. So if I send in a number of Diracs and let the weights just be 1 over n, then what I get is a sequence of Diracs, same number of Diracs, modulo multiplicity, and satisfy the condition. If two tokens coincide on the input, then the tokens need to coincide on the output. Easy to see that transformers need to satisfy that, but in fact, this is generally the case. And in fact, you can remove this condition that they're 1 over n. You can prove that once you have this, it's true for any weights that are positive. Okay. And that leads me to the support preserving map given by an in-context map. So if it's support preserving, and the map between measures can be described as we just introduced, the push forward of an in-context map, then I call that a support preserving in context map. Right? And sometimes we write for this map F as Fg to indicate this in context map. So now we need a strange topology to make actually the conclusion. I introduced three quantities. The measures, the positive measures, will not surprise you. Of course, the variable x that we act on, but also functions psi, continuous functions. I need to do a constructive approximation of what these things mean. I'm going to construct sequences of measures that I approximate on the support by piecewise constant functions to construct actually the in-context map from the property of a map and then prove that it becomes a transformer and the other way around. So I look at the triplet of, well, variables in which the tokens live, the vector space, the measures, and these continuous functions. And I assume that there's a uniform bound on the measure of the set omega. For all the measures, they are bounded by rho over the set omega. And I assume that the psi's are, well, continuous differentiable, and that they satisfy, they have a uniform Lipschitz bound, eta. This eta needs to be uniform bound for all the functions. Then I can introduce a distance function. Wasserstein 1 in the measures, Euclidean in x, and L infinity in the psi's. And then you say, well, this is bizarre, because if I do that, this space is not a complete metric space, because the psi's are continuously differentiable, but we take convergence in L infinity. So indeed, it's not complete, but it doesn't matter for the arguments. And it has to be this way to get the conclusions. It's a technical part. And then I introduce the notion of a regular partial Fréchet derivative of a function as a function of psi. So I'm going to introduce the following. I take the duality between a measure. F maps measures to measures. So whatever F produces is a measure. I take the duality. And the duality means I integrate continuous differentiable functions with respect to that measure. That's what it means. I introduce a finite difference by taking the finite difference in the direction of Dirac x, epsilon divided epsilon. So this looks like a finite difference. But I construct now a set of sequences that converge, sequences of mu and psi, and the psi's are defined to be constant in an open neighborhood with the support of the sequence of measures. And now I take the limit, epsilon goes to 0, and the limit of that sequence, and that generates what I define as the L infinity regular part of the Fréchet derivative of f as a measure. It's a very complicated object. I'm not going into the details here. Suppose you do it for a transformer, a push forward, you work out what this difference is, you get two terms. One term is the regular term, the other part is irregular in L infinity topology. The L infinity means it's L infinity as a map from psi to the derivative with respect to psi of f. And so the story is, if I take a transformer-like architecture, this regular part of the derivative is nothing else, this function psi, subfunction psi, the duality, if you wish, of g mu x. That's precisely what it is. So I split the derivatives into two parts. That's the key part. Only the regular part plays a role. The irregular part doesn't play any role in the closure. That's the key point. Bear that in mind. And then the closure is the following. So this goes in two directions. So if I have a transformer, so the map is described as a push forward, as we did in the first part of the talk. And if it's so that the in-context map is continuous, so here comes the continuity back, then this f will be support preserving in the sense of the definition, and the regular part of its derivative exists, and the map is, in fact, this map is uniformly continuous with respect to this crazy metric that I introduced. Vice versa, if I have a support preserving map with this regular part of the Fréchet derivative being uniformly continuous, then it actually is a transformer. So this is the closure of transformers. So this is the world of transformers from a continuum theory point of view, completely. And well, this is basically what I said over here. And so now you can do one step further. Let me take the continuum limit. And that brings me to the point where we're going to switch gears. If I take the continuum limit as follows, so I take the layers, and suppose that I take the layers on a time interval 0 to uppercase t, so let t be the number of layers, and now I'm subdividing the layers, keeping the interval fixed, I get a continuum limit, right? So I get, in fact, a PDE description of this transformers. What I get is the following. So think of the following, that the multilayer perceptron, I split off an identity and a remainder. Then I can introduce curly V, that is it's the multi-head attention. That is this remainder of the multilayer perceptron, composite identity and attention. Let V be that. So V is essentially the attention on the measure theoretic level. Then a transformer is nothing else than solving this initial value problem. Go from mu0 to mu t by solving the Vlasov equation, where this V appears over here in the Vlasov equation. So here you can see where the push forward comes from. So essentially a transformer is a Vlasov, a solution to a Vlasov equation from the viewpoint of going to an infinitely deep point of view.
This is like a continuity one.
It's like a continuity equation, transport equation.
So what where is the step?
Not yet, it comes. The conservation laws come in a moment. But yes. So
this way of writing the transformer. What is the part of this concern? Is it the mounting of tokens?
So what is conserved, it goes via the in-context map. So the in-context map is in fact giving you the conservation.
Yeah.
Yes. So that is why I actually introduced the in-context map in hindsight to get that conservation. Yes.
Because it maps the tokens.
Exactly.
Which is the same number.
Exactly.
That's where the conservation.
Exactly. That's where it comes from. Yes. And it's inherent in transformers. So this is not a matter. I haven't changed anything. I just did the analysis of transformers. This is basically what they are. And so, but please keep asking questions because this is sort of the point of the talk. Now, you can do a few other things. You may wonder, could I do something else? Well, I could make, this is like first order in time. I can write down a second order in time by introducing a velocity, a phase space, and then I would get something like a Cauchy-Smale system. And if you get a Cauchy-Smale system, you get all sort of interesting dynamics. You get like flocking and so forth. And a lot of problems that are observed in transformers and deep transformers can be associated with flocking mechanisms of Cauchy-Smale in this way. But I'm not going to talk about that here. But you can write a second order version of this, and then you can actually understand flocking dynamics coming out of transformers in a very elegant way. But what I would like to do is switch gears. So Vlasov, the Vlasov equation is not good for physics. That is my point. Vlasov is not like Boltzmann. I cannot via, for example, thinking of it as a distribution and computing moments, as you would do for Boltzmann in phase space, I cannot deduce from it conservation laws that I want to learn. So my point is, this is good and bad news. This is not what you want. And that is sort of where I want to go. Quick sidetrack. You can do beautiful things. If you're just interested in operator learning in physics and you don't want to learn the physics, it's perfectly fine. It's very powerful. So you can introduce graph measures instead of functions, and then you can introduce mappings between graph measures that associate with operators between functions. And in fact, you can generalize things like neural operators that I show over here. So you can actually reduce the regularity of the input function space. You can actually learn operators that work between distribution spaces, generalized function spaces, that you cannot do with neural operators, but you can do with graph measures. And I show an example here of scattering. So you have scatters. I want to, learn the map from the wave speed, the scatters to the solution to the Helmholtz equation, in this case, with a particular source. And here you can see that I, with very high accuracy, actually can predict and learn these maps that I couldn't do with neural operators. And I can actually learn inverses as well, that I show over here. So I don't want to go into details here, but they are powerful for operator learning as they are. So I'm not saying that they have no place, but it doesn't match the physics. And so now I want to come to the Boltzmann story. Let me see. And the first thing, okay, let me see. Yeah, the first thing I want to show is I'm going to change a twist in the architecture, and then I'll come to the Boltzmann argument. And so what I'm going to do is I'm going to be introduced a new architecture that we call flowers or flowers. And what it really does, it breaks this continuity of the in-context map. And so how do we do that? In a nutshell, the rough idea is the following. I'm still creating channels that will act on many heads, as I described before. I'm going to zoom in a little part, a subdomain of the physical quantities that I want to study. And what I do is think of it as channels, but think of it as heads. What I allow is an affine mixing of these. But at the same time, what I'm going to do is, rather than a push forward, I'm going to do a pullback. But I'm going to do a pullback the pullback depends on the function and pulls back the function. Remember, we had an in-context map that depends on the measure, and we push forward the measure with that in-context map. So now we do the other way around and do the dual of that, which is extremely different. I take the pullback of the function where the pullback depends on the function. And so that's sort of what happens. There's a warping in some sense. And what I do is I do that over many, many heads. So you would think of it, that sounds familiar, like what you do in fluid dynamics, semi-Lagrangian approach. You introduce characteristics, and one way of solving it before a shock forms is do exactly that. Well, that doesn't quite work because I don't want to be pre-shocked, but I do it many, many times. So I generalize this idea. And what it does by generalization is actually that I create a collision term in the right-hand side of the equation. That's my claim, and I'll come to that in a moment. But I want to show how it works and that it works. So what happens is that this function, this map is no longer continuous because it can, one head can form shocks, for example. And so I would like to show you, so this is sort of the idea that I have here a pullback, and this row is a network that depends on the input function that's applied to the input function, well, spread over many heads, many channels that have all different heads, and where here the mixing over the heads is introduced. So that is the dual, if you wish, of what we wrote down on the measures with the pullback, for the push forward to the pullback. And then there are some technicalities here. And I want to show you, once you take that different point of view, how it performs. And so here we do a comparison with many, but in particular with Scott and with Walrus over parts of the well data. And in green, you see the second best performance, and in bold, you see the best. So this new architecture doesn't beat everything, but beats almost everything. And it has 2 orders of magnitude fewer weights than, for example, Scott or Walrus has. And so to show how this works in comparison, I think it's nice to show it with some illustrations. So what we see over here is, for example, the viscoelastic instability data set from the well. This was the last input to show how it unrolls, how it forecasts once it's learned. And this is the ground truth. So we go from here to here in the ground truth. Fourier neural operator would do this. And so you can see the errors that it generates. This is the C-next UNet, so sort of reminiscent of the vision transformer. And this is Scott. And this is what this architecture does. And so you can see over here, for example, this whole regime, how much it improves. And over this rollout. So I'm showing here in particular rollout. We did many other tests that you can see. This is a much more strenuous test, so shear flow. And so we go, for example, unroll and predict, in this case, 50 time steps ahead. So this is the input. This is after training. This is the output that the ground truth. The neural operators completely fall apart. C-next falls apart. Scott is trying. We are not perfect, but we're an awful lot closer to the ground truth than any of the others. So my claim is by switching the architecture from this viewpoint is essential in doing these problems in physics. Here is 3 dimensions, Rayleigh-Taylor instability. Same story. This was the input that we used to then roll out 10 time steps. This is the ground truth. This is the Fourier neural operators, completely lost. C-next, not impressive. And here you see how close we get in 3 dimensions, this Rayleigh-Taylor instability. So I want to make here the claim that to revisit this can give an essential improvement even over the state-of-the-art, if you call it the state-of-the-art Walrus, that they have been doing on the well data set. And so here, I want to explain a little bit from an architectural point of view how this works, and then I'll wrap up. So my claim is we need to go back and think Boltzmann. So this Boltzmann, the standard Boltzmann model. So introduce here a distribution of particles. I switch to phase space. That's very essential. So don't work in tokens, X, but lift the tokens to phase space. That's a fundamental part, and that I don't want to underestimate. So the measures now become densities, right? Particle distributions. That is a simple transition. And so the key thing is here you see the transport and a collision term. And the collision term classically is, well, you have pre and post velocities. This is the collision partner. These are the distributions before and after, standard Boltzmann representation, and B is the Boltzmann collision kernel. I won't go into the whole story of the Boltzmann theory, but it's a standard Boltzmann model. But now this doesn't help us, right? Because we cannot represent in a network a collision term. But now we're going to follow the Nambu formalism, the Nambu theory, that generates stochastically the solutions to the Boltzmann problem. And how is that done? How do I translate Nambu into our world? Is I introduce zt, that's going to be the velocity of a particle at time t. I'm going to remove the role of the collision partner, and I, not Nambu, I should say, introduces a jump process, a Poisson random measure. And that random measure will mimic the collisions as a measure. And so again, this comes from Nambu. This doesn't come from us, but I'm going to merge this, what I just talked about. And so how does that work? So I can create essentially a stochastic equation for the particle velocity at time t that is driven by a jump process. And I have a typo here, I apologize. This Poisson random measure that should be described here by n, I mixed up n and mu here, is described as follows. You start with an intensity measure that acts on time as a function of time. The collision partner that you do not know, you do not take into account, the output direction of the velocity, an auxiliary thinning variable that can be written in this form. This is related to actually the distribution that appears in the Boltzmann equation in this form. This intensity generates a Poisson process. This shouldn't be n, and this should be n. And that Poisson process gives you a distribution over a Poisson random measure that is this quantity over here. This omega is the n over here. I apologize for that. According to this law, this is a standard Poisson process. So you put that in here, and this essentially is a characteristic equation. And this equation, in fact, if I integrate this equation stochastically, my claim is will actually generate the in-context map. But what happens in the meantime? Described over here. So this is sort of what happens. This is what we did before, and this is what we get now. So what we do is we have a characteristic equation that is a stochastic equation that gives me the times at which the particle velocities change of one particular particle path. Initially, I pull the velocity from the initial distribution of particles. Then, in fact, the evolution of that, I'm going to augment the distribution, that is the density of a measure now, from Boltzmann, with the Poisson random measure. And I can write the time involution as a push forward of solving this characteristic equation, which is exactly like solving this equation for the in-context map that came from Vlasov. But here's the augmented Poisson random measure. I put an identity here to push forward with this measure. So it is exactly the form of an initial measure and a push forward as in the other case. And so the deterministic world of in-context mapping has become stochastic. That's basically my claim. By augmenting the measures to a density with a Poisson random measure. And in fact, the solutions of the Poisson equation can exactly be generated in this way. So this is the viewpoint where you change transformers to a new object that have a stochastic element in them in a very peculiar way. I know that this Nambu proved that will converge to a solution to the Poisson equation, and hence, via projections, taking moments that I can learn, I can regenerate physical laws. That is my claim. And that's I would like to end the story with. And I'm going to take a slightly, again, I'm going to show you an architecture that is a simplification of the general scheme, like the previous one were. We don't have all the general architectures yet. I showed you one route, now I'll show you another route that we call nerdy. Here I take a different viewpoint. I take the BGK collision kernel. So that's a thin description of the collision process, where I describe the collisions by an equilibrium map. So the collisions are described by F minus an equilibrium map, where this is again the BGK kernel, and tau is the relaxation time. And then the quantities can be generated via projection, classically via taking moments, that I call a decoder. And what I do is the original conservation laws that I'm interested in, I lift via an encoder to phase space to a density. So that's sort of the viewpoint I take. So this is sort of the picture. This is the Boltzmann picture. So here I have a Boltzmann picture where I look at the BGK collision kernel. And in fact, I can solve this as a function of time and take the moments and in fact solve conservation laws. We need to hydrodynamics, granular flows, Navier-Stokes, all these equations in principle. Now, how is it done? Via Lattice Boltzmann models. How do they do that? They discretize the velocities, continuous velocities in phase space on a lattice, say C1 to CQ. So this becomes a vector. And so now we have a mesoscopic picture that not only do we discretize now on the lattice, but we do an operator splitting splitting the advection from the collision. I do first a collision and then a streaming, that's the advection. So what I get is a story where I have the physical quantity, I lift to phase space, but not this phase space on a lattice, an unknown lattice, but it exists, a high-dimensional phase space. Then I have a collision that I need to learn, I have a streaming that I have to learn, I have a projection that I have to learn, that classically will be moments. And so that sort of mimics the physical laws, and that can be described in analogy to what I just described a moment ago. And so then there's some interesting observations that followed. So let me follow this idea. What did people classically do in Lattice Boltzmann? Well, perhaps the most celebrated way to find the equilibrium map was done by Livermore, that we call the Livermore closure. The Livermore closure had the form, roughly speaking, that I can translate in a learned framework by learning two functions that depend on the decoding distribution, the physical quantity, and the lattice, take the dot product, and exponentiate it. So now I say, could all these things are networks, right? This is a decoder and this is a network. How is it done? By abstractly introducing an entropy. Well, now I do it abstractly. I do a transition from the continuum velocities to the lattice that is done with certain weights. You can think of Maxwell distributions or quadrature weights. And I get the KL divergence of the distribution with respect to these weights. That gives me an abstract notion of entropy. You minimize that to that constraint, and that gave Livermore essentially the solution. That's the analogy in the network to what Livermore did, to be very precise. What is this? This is nothing else than cross-attention. So feed it, the velocity is the distribution, I take the dot product, this becomes a soft max, and out of it comes the equilibrium. So in fact, cross-attention is hidden back into this network. And that's the basis of the nerdy architecture. And of course, the streaming can be written as a convolutional network on a graph. So that is a triviality. And so it gives me an end-to-end network. And does this work? So again, yes, it works remarkably. It begins to work where transformers do not work. So in this case, what happens is the training happens on the physical quantity. I give it, so it's the fine-tuning, I give it a movie of a piece of physics, say in this case fluid dynamics. But where it actually learns is on the kinetic level. It predicts on the kinetic level, but it learned a projector, and that is why indirectly it projects the physics. So it trains and predicts in the two different domains, in a macroscopic and mesoscopic level in the network. That's how it works. Let's first look at this case where I show a movie up to a certain time, and then I check via this fine-tuning whether it's learned the physics, and when it rolls out, whether it rolls out in the right way. So does it predict what happens next? And so I showed it here in the cylinder case, supersonic flow around the cylinder, but of course you have shock formation. And so in this case, in fact, I go straight to a more advanced case. I show it the movie up to, say, 150 time steps. I skip, in fact, what happens, and the network gets fed time step 900 and then rolled out to time step 1000. So this was completely blank. And so the only thing it saw, this was the last time it saw. On the right, you see the ground truth, and here you see what this network actually predicts. It's almost indistinguishable. So this is sort of how far you can push it. And if I have 2 minutes left, I want to show you one other thing, and that is a story that I'll be short about. There's one problem if you want to do these sort of experiments, going back to tokens. In the end, we have training data that is finite dimensional. In the end, we sample observations. So if I want to actually do this in physical conditions, where it's very hard, and fluid dynamics is very hard, the unrolling for long times will derail, no matter what your architecture is, unless you intervene. And the idea is here, in this nerdy architecture, we need to impose the second law of thermodynamics. And the way we do this is we're going to go back to this abstract notion of entropy, this KL divergence, and we want to introduce a quantity, a network inside via convex mixing that by training it learns to satisfy the abstract H theorem, the abstract notion of entropy. And surprisingly, I will not go through the details, that element exactly coincides, how to do this, exactly coincides with a deep equilibrium model. So inside the cross-attention sits a deep equilibrium model. And what we can do is we can train it to enforce abstractly the second law of thermodynamics. Why is it important? Well, this allows us to mimic the transfer of energy to unresolved scales and prevent pileup. This is essential because the network cannot do magic. If I give it finite data, there's no way it knows anything more than the finite data. So you need to protect the network from that point of view. And that makes a huge difference in the rollout. And this is how it's done. And I show you two examples. First, let the movie run for 5,000 steps and then predict 5,000 steps. I do that for the Kelvin-Helmholtz rollup and vortex merging test for Reynolds number 50,000, which I don't think any network has shown results at these sort of Reynolds numbers yet. You have nothing to compare it with. And here you see what happens. So this is, on the right is always the ground truth. This is 100 time steps predicted. And so here we go to about 2,000 time steps, 3,000 and 4,000 time steps ahead of from the last time it had seen. And as you see, it's almost indistinguishable from what this is a direct numerical simulation we compare it with, by the way. That is our ground truth. And this is the case if you have a gap, same thing. So even with the gap, it performs extremely well via this protection. So I think my time is up. I would like to make a sort of bold statement that foundation models in scientific machine learning specifically, I think should not just try to approximate physics because they have difficulty doing that. They should reflect physics with architectural components that emerge as phases of the underlying laws. And that's basically the moral of the story. And many things to be done. I showed you only two architectural beginnings that follow the idea of replacing a context map. But of course, the goal will be to replace the context map in full glory using the non-book characteristics. And that's to be continued. Thank you. I'm happy to take questions. Yes.